Hi there, Miss Barber here. In this lesson titled Modeling with Exponential Functions, we will examine processes that can be modeled with exponential functions. These processes include population growth, radioactive decay, bacterial growth, heat diffusion, and numerous others. To that end, the learning objectives of this lesson are: 1. Be able to solve exponential growth applications such as doubling time. 2. Be able to solve exponential growth applications, specifically relative growth rate. 3. Be able to solve exponential decay, such as radioactive decay applications. And 4. Be able to use Newton's law of cooling to solve applications. Roman numeral 1. Exponential growth, doubling time. The initial size of a population is n sub naught, and the doubling time is a. Then the size of the population at time t is given by the equation n of t equals n sub naught times 2 raised to the power of the quantity t divided by a, where a and t are measured in the same time units, minutes, hours, days, years, etc. Suppose a community's population doubles every 20 years. Initially, it is a 500-member community. Find a model for the community's population after t years. The reading of the problem tells you we are working with a doubling problem because it says doubles. So the formula for doubling using exponents is n of t equals n sub naught 2 to the power of t over a, where n sub naught is the initial population, and we read that the initial population is 500. A is the factor in which it doubles, and so it's every 20 years. Now with those two pieces of information, let's build our model. N of t is equal to, we put in 500 for the n sub naught, and then we raise that t to the power of t divided by 20. Be careful not to attempt to multiply the 500 with the 2. Now let's go to part B. How many community members are there after 30 years? So we need to solve the exponential equation we have just obtained for t equals 30. So we've got n of blank equals 500 times the quantity 2 raised to the power of 30 divided by 20. We put in 30 every place there was a t. This number is kind of meaningless, so we'll need to compute it using a calculator. So let's do that. We are looking at the screen of a TI-84. We need to compute the value, which was 500 times, so let's key in 500 times, then we have 2 raised to the power of, and we'll put in parentheses. You can do just 3 halves, but I'll go ahead and put in 30 divided by 20, close parenthesis, and press enter, and we get 1,414.213562. And the population will round to the nearest whole number is 1414. It ought to make sense to you that if it takes 20 years to double, that means 20 years to go from 500 to 1,000, then 10 more years after that should be over 1,000 in the community. When will the population of the community reach 10,000? So now we take the equation we previously obtained, which was n of t equals 500 times 2 raised to the power of t over the doubling time, which is 20 years, and we want to get to 10,000, so we'll do 10,000 equals 500 times 2 raised to the power of t over 20. We've got to get the exponential expression isolated, so let's divide by 500 on both sides. Then you get 20 equals 2 raised to the power of t over 20. Now, if you have an unknown in the exponent, then we need to use logarithms. And in this case, you have to use either the ln or the log, because those are the values on your calculator. Let's do log. Common log 20 is equal to common log 2 raised to the power of t divided by 20. Let's change that exponent to a coefficient. So now we've got log of 20 is equal to t divided by 20 times the log of 2. Now, the log of 20 is one number. You cannot separate the word log from 20. With that said, let's solve for t. So let's divide log 20 by log 2. Then we'll get log 20 divided by log 2 equals t over 20. And then we'll solve for t. That means multiply through by the 20 in the denominator. So we have 20 times the common log of 20 divided by the common log of 2 equals t. And we'll need to compute this number on a calculator as well. So back on the calculator, let's begin with the factor of 20. 20 times, then we'll need log of 20. Let's close that off, divide that by log of 2, close parenthesis twice and press enter, and the number that we get is 86.4385619. So let's record that answer. It'll take about 86.44 years for this community's population to reach 10,000. Roman numeral 2, exponential growth, relative growth rate. A population's relative growth rate, R, is the rate of population growth expressed as a proportion of the population at any time. A population that experiences growth increases according to the model N of t, where N of t is the population at time t. N sub naught is the initial size of the population. R is the relative rate of growth expressed as a proportion of the population, and t is equal to time. This relative growth rate formula is exactly the continuously compounded interest rate formula. The variables have been renamed, but otherwise it is exactly that same formula. The initial population of a colony is 800. If the colony has relative growth rate of 15% per year, find a function that models the population after t years. The relative growth rate is our hint that we need to use the relative growth exponential formula. So that's N of t equals N sub naught e raised to the power of RT. N sub naught is the initial population, and that's 800 in the colony. And R is the relative growth rate. So expressing 15% in decimal form is 0.15. So the formula, or the function, that models this growth is N of t equals 800 times e raised to the power of 0.15t. Roman numeral 3, exponential decay. The rate of decay is proportional to the mass of the substance. Physicists express the rate of radioactive decay in terms of half-life, which is the time it takes for a sample of substance to decay to half of its original mass. The radioactive decay model states that if m sub naught is the initial mass of a radioactive substance with half-life h, then the mass remaining at time t is modeled by the function m of t equals m sub naught e to the power of negative r times t, where r is equal to the natural log of 2 divided by h, and that is the relative decay rate. Radium-221 has a half-life of 30 seconds. How long will it take for 95% of the sample to decay? This is a radioactive decay problem, so let's use a radioactive decay model. That would be M of T equals M naught, which is the initial amount, E raised to the power of negative RT. And for half-life, the rate is determined as ln of 2 divided by h, which is the length of the half-life. So we would write this as ln of 2 over 30. We could get a decimal approximation, but let's just wait till the very end to put it in the calculator. Now, the other thing that's tricky is we're not actually given an initial amount, but it's relative, so we'll just assume, we'll just let the initial amount be 1. That's what we start with. And we want to know how long it'll take to have 95% of the sample decay. So that means we want 5% of it left. So we'll have 0.05 equals e to the negative. The r is ln of 2 divided by 30 times t. Now, let's use the natural log, because the natural log with base e cleans up very nicely. So we'll get that the natural log of 0.05 is equal to negative of ln of 2 divided by 30 times t. We need the t by itself, so solving for t, we would have the ln of 0.05 divided by negative of the ln of 2 over 30. Let's use the calculator to compute this number. This is a TI-84 calculator screen. We're going to use the natural log. I'm going to do this a little bit differently, so let's note. I'm going to say let's find the divisor first. So ln of 2 and divide that by 30. So that number times -1 is the decay rate. Now we'll continue to solve. So let's find the ln of 0.05 remaining. We want that divided by the negative, then we'll of ln of 2 divided by 30. So we'll capture that, and we get 129.657843 seconds. So we'll express the time as 129.66 seconds. So a little over 2 minutes. Roman numeral 4, Newton's law of cooling. If D sub naught is the initial temperature difference between an object and its surrounding, and if its surroundings have temperature T subscript S, then the temperature of the object at time T is modeled by the function capital T of little t equals capital T subscript S plus capital D sub naught e raised to the power of negative k times t, where k is a positive constant that depends on the type of object. Newton's law of cooling is used in homicide investigations to determine the time of death. The normal body temperature is 98.6 degrees Fahrenheit. Immediately following death, the body begins to cool. It has been determined experimentally that the constant in Newton's law of cooling is approximately K equals 0.1947, assuming that the time is measured in hours. Suppose that the temperature of the surroundings is 60 degrees Fahrenheit. Find a function T, cap T of little t, that models the temperature T hours after death. The Newton's law of cooling formula is cap T of little t equals T subscript S plus D subscript 0 e raised to the power of minus k times t. T subscript S is the surrounding temperature, so the problem tells us that the surrounding temperature is 60 degrees Fahrenheit. D sub naught is the difference in the temperature around it and the body of the temperature, so this is going to be 98.6 degrees minus the surrounding temperature, which was 60 degrees. That would give us 38.6 degrees. So let's fill in the parts. The model is capital T of T equals 60 plus, for the D naught we'll put in 38.6, E raised to the power of the constant, which would be negative 0.1947 T. That is the model. Part B. If the temperature of the body is now 72 degrees, how long ago was the time of death? So we are solving for the unknown in the exponent T, and cap T of T is 72 degrees. So 72 is equal to 60 plus 38.6 E raised to the power of negative 0.1947 T. Let's work to isolate the E. So we'll need to subtract 60 from both sides, and that'll give us 12 is equal to 38.6 E raised to the power of negative 0.1947 T. Now we need to divide by 38.6 on both sides, so that would give us 12 divided by 38.6 equals E raised to the power of negative 0.1947 T. Now we can take the natural log of both sides. So continuing, we'll get that the natural log of 12 divided by 38.6 is equal to, natural log of E just gives us the exponent, negative 0.1947 T. And finally, we can isolate the T. We can write T is equal to the natural log of 12 divided by 38.6, and all of that divided by negative 0.1947, which gives us no meaning at all. So let's use a calculator to get an approximate time of death. Let's begin our computation using the calculator. Natural log of, and then we want the quotient of 12 divided by 38.6, close parenthesis. Then we want all of that divided by negative of 0.1947, and we get about 6 hours. How long ago was time of death? About 6 hours.